Hello and welcome to the lesson on relative motion. So our goal today, I want you to be able to determine relative motion of an object when given surrounding conditions influencing an object. So relative motion is kind of it's a neat concept because it's probably something you've never really thought about, but you run into quite often. So frame of reference, which is really what we're talking about in terms of relative motion, it's a coordinate system relative to which motion is described by an observer or described for the observer. So for example, let's look at the snowbirds situation of airplanes flying in formation. If you're on the ground and you are watching this, the formation fly over, you view the planes moving fast, okay? Moving fast overhead. I know exactly, earth-shattering there. But if you look at it from the pilot's perspective, so when the snowbirds are flying that formation, that tight formation, I'm just going to go all delta wings here for the planes, okay, and they look outside their cockpit and look at the plane beside them, it looks like the planes around them are stationary. All right, so if you eliminate frames of reference here, so if they're up in the blue sky, they're performing a maneuver and all they can see is blue sky and they look out, looks like the plane beside them looks like they're parked, looks like no one's really moving. Now, if they're flying low and they can see trees in the background or mountains, they can then discern, the brain sort of sends that signal that no, we are moving here. But when they look out that cockpit and they don't have a frame of reference, and they look at the planes around them, it really looks like they're just hanging there, they're just stationary. All right, so that's what we're looking at today, is how we perceive things and how the brain interprets them, and then what's really happening or the math behind it. So relative motion, this is the formula. I want to make sure it gets onto your study sheet. So relative velocity is VA plus VB. So the definitions here, what does V relative mean? It is the relative motion in the frame of reference. So when we talk about in the frame of reference, we could be talking about you standing at the side of the road. We could be talking about you inside a moving car. We could talk about you falling from an airplane. So it depends on what frame you're in when we're talking about relative motion. All right. The VA in the formula represents the motion of an object in ideal conditions. So we are looking at under no influence. So what that really means is without wind, so a plane is flying or can fly 200 kilometers an hour. That's without taking wind into effect. Or no current, so without current. So a boat is rated to go 80 kilometers an hour. Well, that would be in still water, okay? So it's the motion of the object in perfect conditions. And then finally, VB. VB is what is affecting that motion, and that's where your wind and your current comes into play. So wind, I don't know why I have quotes on there, current, excuse me, etc. All right, so there is your equation and factors when we're talking about relative motion. So I have a little chart here for us to fill out, just to give you a feel for how we perceive things. So let's have our bus. Let's keep the numbers simple here. Let's say the bus is doing 80 kilometers an hour. It's a vector, so it tells me it's going to the right. Let's have the train doing 100 kilometers an hour to the left. And we're going to move the car to 120 kilometers an hour, also to the right. So for this chart here, we're going to move us around. So we're talking about you, the observer. So your location then, we will go bus, we will go train, car, and then for argument's sake, let's go side of road. All right. All right, so what do we observe here? So if you're in the bus, I'm not going to really talk about the bus when you're in the bus. If you look out the window at a train that you're passing, what will it look like when you're on the bus? So let's pretend you're at the very front of the bus, you're looking out the front window and the train's coming at you. Does it look like the train is doing 100 kilometers an hour? No, it's going to look like it's doing 180 kilometers an hour towards you. So let's go to the left, all right? Because the bus, according to our arrows, bus is going to the right. So your perception is the train is coming at you at 100 kilometers an hour. Your brain doesn't discern the fact, oh, I'm doing 80 and the train's only going to do 100. When you look at that train, it looks like it's doing 180 kilometers an hour. Now what about the car? The car, if the car passes you, so let's say you're looking out the window staring at the car, and you've done this before when you're driving on the highway. Even though the car is going 40 kilometers an hour faster, that's all it really looks like. All right, it passes you, it's a very slow pass, so it doesn't look like the car is going very fast. So when you're looking at that car, it looks like it's only doing 40 kilometers an hour as it moves by you. You don't actually see it doing 120 because in your head, your brain isn't telling you, oh, I'm already doing 80, so you need to tack that on. It looks like the car is doing 120. You look at it and see it doing really 40 kilometers an hour. So frame of reference, we're in the bus. Second line here, let's pretend we're in the train now. Train. So the train, if you look at the bus, it looks very, very similar. You're at the front of the train, you see the bus coming at you. It still looks like you're doing 180 kilometers. The bus is doing 180 kilometers, but now it's going in the direction to the right. So it looks like the bus is hurtling at you at 180 kilometers an hour. Inside the train, not going to worry about that. Now what happens when the train and car interact? Well, now if you're sitting in the front of this train and you see the car coming, your brain tells you that the car is doing 220 kilometers an hour to the right, or that's how you perceive it. Okay? Now let's move into the car. So we're in the car and you pass the bus. Well, it looks like the bus isn't going very fast. In fact, it looks like it's slowing down or backing up at 40 kilometers an hour to the left. All right, so when you go and pass something, if you're just going a little bit faster than another object and you watch it out the window, it simply looks like it's backing up. Now when it comes to the train, same idea as we dealt with before, except now you're in the car. If you are driving parallel to the train tracks, it looks like the train's hurtling at you, or your brain believes it, at 220 kilometers an hour left, because your brain has you sitting in the car, that's your frame of reference, and every other object around you is moving. And then, like I said, I'm not going to be in the car. Now, if you're on the side of the road and these objects pass you, your perception is exactly as they're moving. 80 kilometers an hour to the right, train is doing 100 kilometers an hour to the left, and finally 120 kilometers an hour to the right. Because your frame of reference, you're on the side of the road, you're stationary, and your reference is from that stationary point. So that's why we have that formula, V relative equals a VA plus VB. It takes into account your motion as well as the motion of the objects around you. So a couple of examples, and they seem like simple examples, but when you do the math, you got to keep things straight here. So we have a runner can run at a rate of 0.5 meter per second on still ground, head straight north, and for some reason there's a conveyor belt that's 0.4 kilometers in width. If the conveyor belt's velocity is 0.15 meters per second east, determine. So if you run into this situation, it's going to be fairly bizarre seeing a 400 meter wide conveyor belt, but putting that aside for the moment, how long does it take to cross the conveyor belt? So here's our conveyor belt. And the conveyor belt is moving toward the east at a velocity of 0.15 meters per second. And you're going to run north, it says, and you're going to head straight north across the conveyor belt. So you can run at 0.5 meters per second. So A part is how long does it take to get across the conveyor belt? Well, it doesn't really matter that the conveyor belt is moving east or west. You are only moving at 0.5 kilometers an hour north. And that's all you can do north, and that is in the direction you want to go. So for A here, it's simply, get the right formula here, distance equals velocity times time. There's no acceleration, and we already know the distance. The conveyor belt's 0.4 kilometers in width. you can do 0.5 meters per second. So the time it takes for you to cross this is 0.8 to 0.8 seconds. Well, hopefully most of you are saying, hey, wait a minute there. Get those units right there. Right, so 0.4 kilometers, remember delta D, 0.4 kilometers, we want to be all in the same units. That's 400 meters. Hey, welcome to the party, brain. So there we go. So that takes 800 seconds for you to cross that width. So therefore it takes 800 seconds. All right, now B part. You have a friend, they want to pick you up. So how far down the conveyor should their friend park to pick you up? Well, if we look at that diagram, we know that you're not going to end up straight across. You're not going to end up at this location. The conveyor belt is going to move you down to the east, it says here. So that means that your relative motion, and what we can do here is we know that we want distance here. So we know we're going to travel. So maybe I'll write it out here. Travel time is 800 seconds. All right, so our delta D then, so our distance will be, and I'm going to write this as a vector. So if we do the 800 times 0.5, so kind of, I don't want to skip too many steps here. Keep you with me here. I'm using this formula here. Displacement equals velocity times time. All right. So in the I direction, so I'm going to use vector notation. Whoops, it's going to be actually, yeah, I and then J. So in the I direction, which is, in this case, toward the east, all right, my velocity is 0.15, and the time is 800. In the J direction, I know it's half a meter per second for 800. So that would mean my displacement then is 400 J, which makes sense. That is how far it is across the conveyor. And 0.15 times 800, that would equal 120. So there's my displacement vector. So to answer the question, how far down should the friend be? So therefore, you will be moved 120 meters east. And did you have to do it in vector notation? No, definitely not. But I'm just showing you the components here, because what we want to look at in this last stage then is what is the runner's velocity. So what's the runner's actual velocity? So our velocity, I'm going to write it as a vector. So the velocity vector will be 0.15 I. So that's heading toward the east, plus, because we're moving north, half, or 0.5 J. So there is our velocity vector, and it's our relative velocity vector. All right, so let me explain that for a second. We know V relative equals VA plus VB. So if I break this apart, VA is how fast can you move with nothing bothering you. So you are heading straight north, so that means you didn't go east, but you did go 0.5 north. So that's my VA, plus what's influencing me, what's affecting me? Well, the conveyor belt's running to the east and not moving at all to the north. So if I add those two vectors together, I end up with what I had on top. I end up with my 0.15I plus the 0.5J. So now to find my relative velocity, magnitude of relative velocity, we just use our magnitude formula and we get 0.52 meters per second. And then to find the angle, theta equals, and I'll finish this up in the next video and get through the examples. I just don't want to rush through here, so it gives you a clean break.